So here we are. Okay, very good afternoon to everyone. Today we will be having the revision one on unit number 3. So we have completed unit number 3. Last lecture of unit number 3 was what we saw about different programming concepts like interfacing of peripherals with C, interfacing of how different interrupts are interfaced, how different interrupts can be used. All these things we have seen in the last lecture of unit number 3. So now actually we are going to have the revision of unit number 3. Before going to the revision, there are a few things which I'd like to request you. It's a request that I've given you a Google form in order to fill up the information. Yes, have you got that form, students? Hello.
Yes, sir.
You have got the form, a Google form I have given, and that Google form you have to fill it. And up till now, only 28 students have filled that form. That is all the information of yours, like right starting from SSC 12th mark sheet, then whatever the conferences or seminars or workshop you have attended, all those things are in that. So that information is required not only for NAC but also for the alumni updation as well as for the record, departmental record. So everyone is requested to fill that form as soon as possible. It's not that as such as big, because if you have all the soft copy documents with yourself, it just need to upload that. So this is the first request to you. And second request is that now the tutorial you have to upload. So exactly on the tutorial day, I will be giving you the link of Google form, and where you have to upload your tutorial. So tutorial 1 and 2, tutorial 1 will should be uploaded on this coming week, and tutorial 2 will be in the next week. So these are the two things which I would like to request you. So please hurry up and fill that form, Google form, as well as the scholarship forms also, because still 10 to 10 plus people have not filled the scholarship form. So I do feel so they should fill it. Now we will start the revision one. So this was the introductory part of ARM. So ARM Holdings is nothing but a fabless semiconductor company that develops processor system on chips, software, etc. ARM, actually full form of ARM, is an advanced RISC machines, which was invented in 1990, and whereas RISC is the main CPU design strategy implemented in its processor. Today, the ARM processors are found in almost any domain like handheld devices, consumer electronics, robotics, automation, etc. Processors that has been developed from ARM Internet Protocols IPs are used in embedded systems like smart TVs, smart watches, smartphones, tablets, computers, etc. Then this advanced RISC machine, or we also said can be saying it as an ARM processor, is defined as the family of the CPU that have wide usage in the electronic devices such as smartphones, wearables, tablets, multimedia players, etc. So ARM was actually specially designed for the mobile, as a mobile processor, but afterward it started having different applications. Then what about ARM core? So why the ARM is so important? Because they can be designed specially for embedded systems. The need of embedded systems can be satisfied only if the feature of RISC and CISC are considered together for the processor design. So we know that ARM architecture is not a pure RISC architecture. So RISC is nothing but reduced instruction set computers, but it is a blend, means it's a mixture of RISC and CISC features, where RISC is a reduced instruction set computers, CISC is a complex instruction set computers. So let us see about this RISC and CISC architectures. It is a type of a category of a processor or instruction set architecture. Now, it is a medium whereby a processor communicates with the human programmer. An instruction is a command given to the processor to perform an action, and instruction set is nothing but the entire collection of all the instructions taken together. And architecture means a particular way of building the system that makes the processor. So this is about the terms that are related with RISC and CISC. Now let us see what RISC means. It's an reduction instruction set computers. The main idea behind is to make the hardware simpler by using instruction composed of few basic steps like loading, evaluating, storing operation. Just like load command will load the data and store command will store the data. So यहाँ पर individually काम होता है. जैसे फॉर एग्जाम्पल उसको लोड करने के लिए बोला तो वो लोड करेगा, इवेल्युएट करने के लिए बोलेगा तो इवेल्युएट करेगा, और स्टोर करने के लिए बोलेगा तो स्टोर करेगा. सो हर स्टेप को अपना डिफरेंट वे से इंडिविजुअली आप इसको execute कर सकते हैं. So that is why the RISC is a simple. It's hard, that makes hardware simple for the instruction. But in case of CIC, what happens is that it's a complex instruction set. That means if a single instruction is given, it will not only load, evaluate, but store the operation. Just like multiplication command will do the stuff of loading the data, evaluating the data, and storing it, and hence it is complex. So RISC is makes the hardware simpler, whereas the CIC will make it complicated. RIC will execute each step by step, but CIC will execute in only single instruction. That will it will not only load, evaluate, but also store the operations, and hence it is called as complex instruction set computer. So now let us see that what are the features that are benefited to the embedded systems. Why the ARM core is specially used for designing the embedded systems. The first feature is the high performance. It ensures that the system has a fast response. Then low power consumption. It makes the system more energy efficient. Low silicon area. It reduces the size and consumes less power. These are the two most important features that benefits the embedded system the most. One is the system more energy efficient and reduce the size and low power consumption. Yeah, consumes less power. Then high code density helps the embedded systems to have less memory footprints. Then load or store architecture is used to load the data from memory to CPU, or store the data from CPU register to memory. That means enable the memory access whenever required. And the sixth one is the register bank, which is having large number of working registers. That will also benefit to the embedded system, as it is required to perform most of the operations within CPU and provides faster context switching in multitasking applications. So registers are very, very much important. So these features of ARM really benefits to the embedded systems, and henceforth, therefore, it is much more suitable. This ARM core is much more suitable to the embedded systems in designing the embedded systems. Then this is the basic ARM architecture. So you can see that there is an address register, program counter, incrementer. There is a register bank. Then you have a multiple register. Then A bus, B bus. Then a barrel shifter. Then it is having the ALU. Then there is a data out register, data in register. Then there is a control, and then there is an instruction decode and control. So all these things are very much useful in designing the ARM architecture. So this is overall general ARM architectural point of view. Now, what does it have in it? The ARM Cortex M3 can be understood from ARM processor and the architecture. So Cortex M3 is a special ARM processor, but it can be easily understood with ARM processor and architecture. The register bank, there are 16 general purpose registers from R0 to R15, and there is a current program status register, that is PSR, which are accessible by the user application. It has almost 20 numbers of banked registers, specifically used for different operating modes of IAM core. These are invisible to the user applications. Then the register bank has also two read ports in order to read operand 1 and operand 2, as well as write port in order to write back the result of the operation to any register specified in the instruction. It has additional bidirectional port to update the program counter. It has additional bidirectional port to update the program counter with the address register and increment. So all these things features are in the architecture. Then the address register is incremented at every sequential byte accessed by the incrementer, but the program counter is incremented by 4. So in the ARM state of the core, and the program counter is incremented by 4, whereas the arm state of the core is incremented by 2 in thumb state of a core. Then address register is directly connected to the address bus. The barrel shifter can shift or rotate operand by a specified number of bits prior to arithmetic or logical operations. Then 32-bit ALU performs arithmetic and logical operations. Then data in, data out registers hold the input and output from and to the memory. The instruction decoder and associated control logic generates appropriate control signal for the data path after decoding the fetch instructions. The MAC is also there, that is an used to multiply two register operands and accumulate. So memory accumulate with the another register holding the partial sum of the product. The encoded instruction byte of the program are saved in the code. Just a moment. Okay. Okay, so after the instruction is decoded, appropriate control signals are generated by the data path, and the required registers are activated in the register bank and operands low out from two read ports in the register bank to the ALU. Operand 1 and operand 2. So operand 1 will go through the A bus and operand 2 will go through the B bus after pre-processing at the barrel shifter. The result of the operation at ALU is returned to result register through write port at register bank. You always remember that the two operands can be read with the help of two read ports, and the result can be stored in a result register through write port in the register bank. That is the most important thing which you have to understand. For load or store instructions after decoding the instruction, the data memory address is first calculated at ALU, and as specified in the instruction, and pointer register is updated to the register bank. See, for loading the instructions after decoding the instructions, the data memory address is first calculated at ALU, and then as specified in the instruction, and then a pointer register is updated at the register bank. So pointer register ऊपर की तरफ जाएगा. The address in the pointer register is given to the address register to access the memory and transfer the data. If it is a load multiple or store multiple instructions, the core does not halt before completing the required number of data transfer unless it is reset exception. जब तक reset exception देता नहीं तब तक वो halt नहीं करता है. Now we'll go to that was completely an ARM Cortex architecture. Now we'll go for this ARM Cortex series classification. So basically there are three types of ARM Cortex. One is A, second one is R, and third one is M. So A is nothing but Cortex application, R is nothing but Cortex real time, and the third one, Cortex M, is mainly based for the microcontrollers. Cortex A is built for advanced operating systems and exhibit the highest possible performance. It is built for advanced operating system. That thing you have to remember. Cortex R caters perfectly the need of real-time applications. So it is useful for real-time applications and provides its user with a faster response time. And M is specially been built for microcontrollers. And this is how the performance functionality versus capability of ARM Cortex is given. So you can see that there is a rise of Cortex M0 to M4, then there is a Cortex R, so R7, R5, R4, then Cortex A5, A7, A8, A9, and A15. And here in the embedded Cortex processor, application Cortex processor is that one, whereas the embedded Cortex processor is ARM7, ARM9, and ARM11. So these are the two different types of classifications we can see here. So this is how the Cortex A5 to A57, that is an application, Cortex A application, high performance, full OS support, smartphone, digital TV, etc. Then Cortex R, that is a real-time application, high performance, automotive braking systems, etc. And the Cortex M series, that is from M0 to M4, is a microcontroller built-up processor, which is a cost-effective solution for microcontrollers. Then we'll see Cortex A series. This Cortex A category of a processor is specially dedicated to Linux and Android devices. So you can see that whenever there is a Linux and Android device, so that means Cortex A series ARM processor is being used. Then any devices starting from smartwatches and tablets and continuing the network equipments can be supported by Cortex A. So it is the form of basis of A5, A7, A8, A9, A12, A15, and A17 processors. The main feature of the Cortex A is a top performance and brilliant power efficiency. So this is how the A belongs to. A5, if you go sides, it is the smallest processor and it but can still demonstrate multi-core performance. A7 is somewhat 20% higher in performance as compared to A5, but it is famous for its power optimization technology. Applications include smartphones and tablets. A15, it is finds an applications in high-end devices, low power servers, and wireless technologies. This is the first processor in the range that fits data management and virtual environmental solution. A17 is impressive as the effectiveness. That is why its main aim is to satisfy the need of premium class devices. A15 is the latest series produced by the company. It extends the areas of applications to low power server, demonstrate useful optimizing features, and create great concern from migrating from 64 bits to 34 bits. Then this is the applications of ARM Cortex A series, smart devices, variables, automotive systems, servers and networks, satellite receivers, and home gateways. Then we'll go to the R series, that is a real-time series. Cortex R processor mainly targets the real-time solutions. They find application in controllers, networking equipments, medium players, and other similar devices. The ARM processor provides great support for the automotive industry. Then Cortex R processor have a lot of in common with high-end microcontrollers, but at the same time have the ability to fulfill more scalable tasks. Then in which the first series is R4 series, that's where it is clocked to 600 megahertz. The main characteristics is the dual issue 8-stage pipeline and prefetch prediction. R4 controllers can quickly handle any incoming interruptions. R5 is take care of the networking and data storage. It extends the set of R4 features by adding improved efficiency and reliability. It allows the construction of strong systems with lightning fast response. Then the processors from this category R7 demonstrate a very high performance. It can be implemented, tools can be implemented for lockstep, symmetric and asymmetric multiprocessing. The generic interrupt controller is another significant feature that has to be mentioned. Then the third of the series is Cortex ARM series, M series. This is by far the most important series which we are going to concentrate a lot because M3 series is to be studied in detail in this unit. The Cortex M is known as an industry standard. It finds the implementations in FPGA, integrated memories, and clocks. Each of the design controllers is used to a particular segment of the market, more focused on lower end of the performance scale. They are still powerful when compared to most microcontrollers. M4 and M7 are used in many high performance microcontroller products with minimum clock frequency up to 500 megahertz. The performance is not only the factor when selecting this processor, but low power cost is also very important. The family contains variable products to different needs. So in the series, Cortex M0 is the first one. Very small processor for low cost, ultra low power microcontrollers and deeply embedded applications. Then Cortex M0 Plus, it is the more energy efficient processor for small embedded system with additional features like single cycle IO interface and vector table relocation. Cortex M1 is a small processor again designed and optimized for FPGA designs, same instruction set as M0. Then Cortex M3 is a small but powerful embedded processor for low power microcontrollers that has a rich instruction set to enable it to handle complex tasks easier. It has an hardware divider and MAC instruction. In addition, it also has a comprehensive debug and trace features to enable software developers to develop their application quicker. Cortex M4 provides all the features of M3 with additional it does have two things that it can use with DSP. and also and single instruction, multiple data, and faster single cycle MAC operation. M7 is a high performance processor for high end microcontrollers and processing intensive applications. M23 is having similar all the features of Cortex M0 Plus processor. Beyond that, it is having a trust zone security extension. M33 is also very much by for like a previous Cortex M3 and M4, but with much more better flexibility, design, better energy efficiency, and high performance. It also supports the trust zone security extension. Then we are going to see the overview of a Cortex M3 processor. It is uh, it is one of the first of the Cortex generation of the processor released by the ARM in 2006, and specially designed to target 32-bit microcontroller market. It provides an excellent performance at low gate count and comes with many new features previously available only in high-end processors. जो features high-end processors के लिए थे वो सारे के सारे M3 में आ गए. See, we have to concentrate on M3 because this is going to be the targeted microcontroller, which we have to study in detail. So we have to get all the things about this processor. So first is that it was released in 2006. Then it was primarily designed to target 32-bit microcontroller market. It provides excellent performance at low gate count and comes with many new features previously which were available for high-end processors. Then the Cortex M3 addresses the requirement of 32-bit embedded processor markets in the following way. So these are the things which are with the performance, how this performance of M3 is higher. One is the greater performance efficiency allows more work to be done without increasing the frequency or the power requirement. Low power consumption, then enhanced determinism, improved code density, ease of use, then low cost, wide choice of development tools. So these are the some of the performances. Now we have to move towards instruction set of Cortex M3. इसमें कौन से इंस्ट्रक्शन सेट यूज होते हैं, बिकॉज इंस्ट्रक्शन सेट ही सबसे इंपॉर्टेंट होता है in order to have the performance in order to have the performance very high from this Cortex M3. So two different instruction sets are supported by the ARM processor. One is the ARM instructions that are 32-bit and thumb instructions that are 16-bit. So ARM instructions 32-bit and thumb instructions 16 bits. During program execution, the processor can dynamically switch between the ARM state and thumb state. So दोनों instruction set के बीच में वो dynamically switch हो सकता है. And in order to use either one of the instruction set, so कोई भी एक instruction वो इस्तेमाल कर सकता है. Suppose वो ARM state में instruction use कर रहा है और उसको thumb state में जाना है तो switching कर सकता है. But at a time only one of the instruction set can be used. I'll tell you that how both can be used in the further slide. The thumb instruction set provides only a subset of the ARM instruction, but it can provide a higher code density. It is useful for products with tight memory requirements. So this is how I was saying that you can see that it is having two instruction set. One is your ARM instruction set and the second one is a thumb instruction set. So you can see that the thumb instruction set is of 16-bit, which is inside the thumb 2 technology, which is the combination of 32-bit and 62-bit instruction set. So the thumb 2 technology extends the thumb instruction set architecture ISA into highly efficient and powerful instruction set that delivers the significant benefits in terms of ease of use, code size, and performance. So this figure shows the relationship between thumb instruction set in thumb 2 technology and the traditional thumb. So one is the traditional thumb, which is of 16 bits, then Cortex M ARM state, which is of 32-bit, and the third one is the thumb 2 state, which is having 32-bit and 16-bit thumb instruction set. So this is the difference between the thumb 2 and thumb 1. So thumb 1 is of 16-bit, whereas thumb 2 is a combination of 32-bit and 16-bit thumb instruction set. The extended instruction set in thumb 2 is the superset of previous 16-bit instruction set with additional 16-bit instruction alongside 32-bit instruction. So that's why what I was saying. It allows more complex operations to be carried out in thumb state, thus allowing higher efficiency by reducing the number of states switching between ARM state and thumb state. This is very important. Higher efficiency by reducing number of states switching between arm state and thumb state. उनके बीच में switch हो जाते हैं ताकि reducing the number of states, in order to reduce the number of states. So that will be beneficial in order to carry out the operations. Focused on small memory system devices such as microcontrollers and reducing the size of the processor, the Cortex M3 supports only thumb 2 instruction set. This is very much important. I said that thumb 2 is the most important instruction set. Like thumb 2 is nothing but the traditional thumb, which is of 16-bit, plus the extra thumb that is of 32-bit. So both instruction set together will be used by the Cortex M3. With support to both 16-bit and 32-bit instructions in thumb 2 instruction set, there is no need to switch the processor between thumb state and arm state. ये दोनों भी यूज होने की वजह से उनके बीच में स्विचिंग की कोई जरूरत ही नहीं. The thumb 2 instruction set is very important feature of ARM7 architecture. The Cortex M3 processor instruction set has a large number of new features. For the first time, the hardware divide the instructions is available on ARM processor, and number of multiply instructions are also available on Cortex M3 in order to improve data crunching performance. It also supports unaligned data accesses. A feature was previously been supported or available on high-end processors. Then these are the applications. The first one is the low-cost microcontrollers. Second is automotive. Third is the data communications in industrial control, consumer products. Then we'll move towards the memory mapping. The Cortex M3 has predefined memory mapping. This allows the built-in peripherals such as interrupt controller and debug components to be accessed by simple memory access instruction. The predefined memory map also allows the Cortex M3 to highly optimize for speed and ease of integration in system-on-chip designs. The Cortex M3 design has an internal bus infrastructure optimized for this memory usage. In addition, the design allows these regions to be used differently. For example, data memory can still be put into code region and program code can be executed from RAM region. Overall, 4 GB memory space can be divided into the range shown in the next slide. So this is how the range starts from 0 into 0000 to 0 into FFFFF. So there is code, SRAM, peripheral, external RAM, external device, system level. So code is used mainly for program code. Also provides an exception vector table after power up. Then SRAM mainly used as a static RAM. Then peripherals mainly used as a peripheral. Then the external RAM mainly used an external memory. Then the system level is a private peripherals include built-in interrupt controller, NVIC, MPU control and registers. So this is how the memory mapping of ARM Cortex is. Then there is a bus interface also. The main bus interfaces are as follow: the code memory buses, system bus, and private peripheral bus. So the code memory bus is again divided into two buses. One is called I code and the other called D code. These are optimized for instruction fetches for the best instruction execution speed. The system bus is used. Second one, the system bus is used to access memory and peripherals. This provide access to the SRAM, peripherals, external RAM, external devices, and part of the system level memory regions. The private peripheral bus provides access to the part of system level memory dedicated to private peripherals such as debugging components. Then comes the optional MPU that is called as memory processing unit. This unit allows the access rules to be set for the privilege access and user program access. When the access rule is violated, a fault exception is generated. जैसे access rules को violate हो गया, fault exception is generated, and the fault exception handler will be able to analyze the problem and correct it. The MPU can be used in various ways. In common scenario, the OS can set up the MPU to protect the data used by the OS kernel and other privileged processors. MPU can be also used to make memory regions read-only to prevent accidental erasing of the data or to isolate the memory regions between different tasks. Overall, it can help the embedded system to become more robust and reliable. It also has a debugging support. So Cortex M3 is also having a debugging support. It includes number of debugging features such as program execution control, including halting and stepping, instruction breakpoint, data watch point, registers, and memory access, profiling, and traces. It is based on the core site architecture. The debugging hardware is based on the core site architecture. Unlike the traditional ARM processors, the CPU core itself does not have a joint test action. Group JTAG interface instead of debug interface module is decoupled from the core, and the bus interface is called as debug access port, which is provided at the core level. The debugging support is very much important, as the chip manufacturers also include an embedded trace microcell that allow to instruction trace. So trace information is very much important, as it is one of the most important feature of debugging support. So it not only traces the port interface unit but also debug host, and can collect the executed instruction information via external trace capturing hardware. Within the Cortex-M3 processor, a number of events can be used to trigger the debug actions. In addition to these debugging features, Cortex-M3 processor also provides a flash patch and breakpoint unit that provides a simple breakpoint function or remap an instruction access from flash to different location in SRAM. Now, after memory mapping and debugging support, this is the most important, and that is called as registers. So it has a general purpose registers from R0 to R12, and some 16-bit thumb instructions can only access. So R0 से R12 तक जनरल पर्पस रजिस्टर्स है, और R15 तक वैसे सारे रजिस्टर्स है. R0 से R0 through R2 are general purpose, but some of the 16-bit thumb instructions can only access R0 through R7, whereas 32-bit thumb 2 instruction can access all these registers. So इसका मतलब ये है कि R0 through R12, R0 to R12 है, उसमें से some of the 16-bit instructions can only access R0 to R7. But whereas 32-bit thumb 2 instructions can access all these registers. यानी R0 से R7 तक एक्सेस हो सकता है लो रजिस्टर का 16 बिट के लिए, बट 32 बिट थंब 2 के लिए सारे रजिस्टर्स को एक्सेस किया जा सकता है. सो R13 से R15 तक स्पेशल रजिस्टर्स है, and they are predefined functions and can only be accessed by the special register access instruction. So you can see that from R0 to R12 are the general purpose registers, in which R0 to R7 are the low registers, R8 to R12 are high registers, R13 is the main stack point and process stack pointer, R14 is the link register, R15 is the program counter, then XPSR is the program status register, then primary mask, fault mask, base pry are the interrupt mask registers, which are called as special registers, and the last one is the control register, which is given by control. So this R13 is the stack registers. So R13 is the stack pointer. There are normally two stack pointers. This duality allows two separate stack memories. So दो कौन से है R13 में, एक है memory main stack pointer और दूसरा है process stack pointer. When using the register name R13, you can access only the current stack pointer. The other one is inaccessible unless you use special instruction to move to special register from general purpose register. इसका मतलब मेन स्टैक पॉइंटर ही मेन बाय डिफॉल्ट होगा. अगर आपको यूज करना है प्रोसेस स्टैक पॉइंटर को, तो आपको स्पेशल इंस्ट्रक्शंस देने पड़ेंगे. दैट इज व्हाट इट सेज. दिस इज सो वो किस से दे सकते हैं आप? यू कैन यूज द स्पेशल इंस्ट्रक्शन टू मूव द स्पेशल रजिस्टर्स फ्रॉम जनरल पर्पस रजिस्टर MSR and move special register move register to general purpose registers. So ये move to special register from general purpose register MSR and move special register to general purpose register. So एक है general purpose register और दूसरा है special register. So these two stack pointers are main stack pointer and process stack pointer. Main stack pointer is a default stack pointer, whereas the program stack pointer is used by the base level application code. Stack push and stack pop. That is stack push and pop. Stack is the memory usage model. It is simply a part of the system memory, and the pointer register is used to make it work as first in last out buffer. So first in last out होगा. The common use of stack is to save register content before some data processing, then restore these content from stack after processing task is finished. यानी उसमें से निकाल के रखो, इसको प्रोसेस करो और बाद में फिर अपनी जगह पे रख दो. It is not necessary to use both the SPs. Simple applications can rely purely on MSPs. The stack pointers are used for accessing stack memory process such as push and pop. In Cortex M3, the instruction for accessing the stack memory are push and pop, and the assembly language syntax is given after each semicolon. There is a comment. So this is how the push and pop is given. So push R0 equal to R13 equal to R13 minus 4, which is equal to R0. Whereas pop R0 means R0 equal to memory R13, which is R13 plus 4. So you can push or pop multiple registers in one instruction. This is the link register, which is called as R14 also. Inside an assembly program, you can write it as either as R14 or LR. It is used to store the return program counter PC when subroutine or function is called. For example, when you are using the branch and link instruction, that is called as BL. So this is how the link register can be executed while doing the program. This is the program counter, that is R15 is the program counter. You can access it by either using R15 or program counter. Because of the pipeline nature of Cortex M3, when you read the register, you find the value in different, because 0 को उसमें 4 normally add हो जाता है. So when I say that move R0 PC, that means R0 will become as 1004. So जैसे ही 0 into 100 हो गया equal to mob R0, तो program counter में it is incremented by 4. Special registers, so primary mask, pry mask, fault mask, and pass pry, control register, and program status register. So by using MSR and MRS instructions can be used in order to read the special register as well as write the special register. This is program status register, in which is having the application program register APSR, interrupt program status register IPSR, and execution program status register EPSR. The three PCRs can be accessed together or separately using special register action instruction MSR and MRS. इनको separately भी use कर सकते हैं या together भी. जैसे ये together हो जाएंगे तो वो बन जाएगा XPSR. XPSR. So you can see this. MRS means for reading, MRS for reading, exception and interrupt state. Again, MRS for read, MSR for writing. This is the APSR separately. Then IPSR, exception number separately. EPSR can be separately executed, but in commonly it will become as XPSR. That is, will combine all the three together. Then this is the things. Primary mask base pry registers are useful for temporarily disabling interrupts in timing critical tasks. The fault mask is to temporarily disable fault handling when a task has crashed. Then once the core starts cleaning up, it might not want to be interrupted by other faults caused by the crash process. Therefore, the fault mask gives the OS kernel time to deal with the fault condition. So this is the pry mask, fault mask, and base pry. And how you can read and write all these special registers is given here. MRS जहाँ जहाँ पर है वहाँ पर वो read हो रहा है. MSR जहाँ जहाँ पर है वो वहाँ पर write हो रहा है. This is the control register. The control register is to define the privilege level and SP selection. This register has 2 bit. One is 1 and the other one is 0. So जब जब 1 होगा, it is whenever the control is 1, control 1 bit is always 0 in handler mode, but it is 0 or 1 in the thread or base level. Whereas control 0 bit is writable only in a privilege state. Once it enters the user state, the only way to switch back is to privilege is to trigger an interrupt and change this in the exception handler. So this is how the control can be written. So MRS is for reading, MSR is for writing. So this is how the things are there. Hello. Hello. Hello.
Yes, sir.
Is there any question you can ask, because it's quite a big unit. So if there is any question which you would like to ask, we can go on the slide. What if there is any problem? Have you understood everything whatever I have taught? This was the revision. We have already finished yesterday. Have you got it, or is there any kind of question that you would like to ask? Yes, students, you can ask frankly. Is there any question? Please ask if there is any question. No questions? Okay, we'll go for the attendance. Roll number one. Roll number one.
Yes, sir.
Roll number. Okay. Roll number
Yes,
two.
sir, present.
Okay. Two. Two is there. Three.
Yes, sir. Yes, sir.
Okay. Four. Five. Six.
Yes, sir.
Seven.
Yes, sir.
Eight.
Yes, sir.
Nine. Eight is there. Nine.
Present.
10. 11. 12.
Yes, sir.
13. 14.
Yes, sir.
15. 16. 17.
Yes, sir.
18. 19.
Yes, sir.
20. 21. 22.
Yes, sir.
23.
Yes, sir.
24. 25. 26. 27.
Yes, sir. Yes, sir.
28. Yes. Okay. 28. 29. 30.
Yes,
30.
sir.
Okay. 31. 32. 33. 34. 35. 36. 37.
Yes, sir.
38. 13.
Yes, sir.
39. 40. 41. 42. 43.
Present, sir.
44. 45. 46. 47. 48. 49. 50. 51.
Yes,
50,
sir.
52.
Present.
53. 54.
Yes, sir.
55.
Present.
56. 55 is there. 56. 57.
Present, sir.
58. 59. 60.
Present, sir.
61. 62. Okay. Any other number? Any other number remaining? Is it final? Okay. Thank you. Please call here absent number also.